Good morning, Miss Cheerilee!
Good morning, every pony. I hope you brought your thinking caps, because today we're going to learn about physics.
Physics?
Specifically, the use of force in energy conversions. In this case, using mechanical work to convert potential energy into kinetic energy.
The what now? Miss Cheerilee? That sounds a bit over our heads. Yeah, why would we even need to know that stuff?
Oh, it's very important. In fact, you'll most likely end up...
No, Cheerilee, this is important. Fillies of Equestria, we interrupt your daily scheduled learning time to bring you something of greater importance. Namely, a report on the effect of significant changes of calcium 2 plus ion concentration on the production of ATP within cells.
Pinkie, this is way above their grade level. They won't understand it.
What? Look, they don't seem confused at all. Alrighty, so I was walking down the street one day and thinking to myself, gee, there's a lot of complex intermolecular interactions happening in me. I wonder how they work. So I went to the castle and found a few books on this subject, then I wrote down everything I learned to present with you today.
That's great and all, but why exactly are you presenting it to all of us?
'Cause it's cool! Ahem! 'Cause of all the complex interactions, cells try to maintain homeostasis to function properly. That probably means any significant imbalance in any molecule or ion would affect everything. There's a right amount of calcium that contributes to an optimal ATP production rate, but any significant lack or overabundance of calcium will drastically reduce the rate. But that's just my hypothesis. I don't know that many specifics because it's still new to this molecular biology stuff.
Pinkie, how is this even tangentially related to our current level of education?
So I know what you're thinking. Does ATP production depend on calcium concentration? Yes, it does. Calcium is a key regulator in diverse intracellular signaling pathways and has long been implicated in metabolic control and mitochondrial function. This paper studied the effects of calcium over a broad calcium concentration range and over different respiratory states. Here, we see that free calcium at 500 nanomoles has stimulatory effects on respiration and ATP production in the presence of various planned concentrations of ATP. However, at 10 micromole or greater concentrations, the calcium inhibits ATP production. They even tested mitochondria energized by different substrates. This suggests that calcium-induced inability to utilize potential for phosphorylation when you also take into account the fact that the varying concentrations of calcium didn't have much of an effect on the potential within the mitochondria. This paper and all their experiments determined that nanomolar free calcium enhances oxidative phosphorylation, but too much leads to phosphorylation inhibition. Now, the next paper, Transient Mitochondrial Depolarizations Reflect Focal Sarcoplasmic Reticular Calcium Release in Single Rat Cardiomyocytes, proves that a significant increase in calcium concentration due to the focal release of calcium from sarcoplasmic reticular calcium stores and consequent uptake of calcium by local mitochondria directly results in mitochondrial depolarizations. They confirmed this in their test through various methods, including depleting the sarcoplasmic reticulum stores via long-term incubation in ethylene glycol bis beta amino ethyl N and N' tetrazettic acid, buffering intracellular calcium using BAP-to-IM loading, blocking sarcoplasmic reticular calcium release with iodine, and blocking mitochondrial calcium uptake by microinfusion of diaminopentane pentamine cobalt, which is a novel inhibitor of the mitochondrial calcium uniporter. Wake up! We're not done yet, sillies. You ever heard of Goldilocks? Me neither, but in this next paper there's a Goldilocks effective calcium that occurs on liver mitochondria, where specific just right concentrations of calcium activate oxidative phosphorylation. Just like these other papers, their experiments revealed that high concentrations of calcium around 52.9 micromoles dissipated mitochondrial membrane potential by opening the mitochondrial permeability transition pore, which led to mitochondrial swelling, fracture, and cell death. They found that mitochondria respire better when calcium concentrations are around 2.4 and 22 micromoles. But it doesn't really talk about what happens when there's too little. Most of the stuff I read didn't focus on that. It seems like oxidative phosphorylation is just not as effective. Nothing drastic happens, but hey, that's an area for further research. Anyway, they figured this out using an Ouroboros high-resolution oxygraph by isolating mouse liver mitochondria, adding various concentrations of calcium followed by ATP to induce oxidative phosphorylation, oligonicin to inhibit ATP synthase and measure respiration dependent on the proton leak, and carbonyl cyanide-free chlorophenyl hydrazone. to induce maximum electron transport.
Universally never killing my sissy army. As no me prick my missing geckos to rock young lettuce, see any kais to rest post upon a molecular via blast acting missing with the complex chew to order synthesis inside the animal complex up. Winter she be a miss to see some fresh can so so handy. And wash it bite so young as nested toward disease as a child, so post for the any bite can read Miss OS and hey, post make you fetch you as an appraiser to suit for you like after so dressing magnet coder, right? Pokem chicken is so chubut kash to any calazia. Yes, sweet is the healthy engineer defer to have to zombie take out the sea and that can eat a much miss a canister and AC out the sea opposed of you. Fry still flat able to zack a fibulation cool with the custard. Have a prodigy got via last as a kid, pony but don't be a come well and goods.
Alrighty, next paper. These ponies developed a model to accurately simulate the effect of calcium on cardiac mitochondrial energy production. They also did experiments to make sure their model accurately predicted reality. This is what they were trying to model. And this is one of the equations they came up with. It describes the flux for the alpha-keto-glutarate dehydrogenase complex, which is a thingy that produces NADH. Look, there's calcium in the equation. There and there. Guess I was right about calcium having an effect. Look! Even more calcium! This equation describes the NCX flux, the calcium being mitochondrially extruded. And finally, these are the results. The effective calcium ion on ATP production flux, NADH production flux, and the potential gradients IM. As you can tell, this paper has a drastically different potential versus calcium concentration graph than the first paper I talked about. That could be due to the respiratory states tested or the type of mitochondria used. But there are tons of factors that could be attributed to the difference. Oh, that reminds me, I had a bunch of questions after reading all those papers. Like, what if the type of mitochondria used in the various experiments were from brain cells as if liver or hindlimb cells? Or what if some other factor like the concentration of magnesium in the cell was varied and the resultant calcium concentration versus ATP production rate was determined? How about we glue the mitochondria together so they can lose their potential gradient and then see what a super-duper high concentration of calcium would do to it? What if we do the thing and using the phrase experiment order from 4 choice cells instead of liver, hindlimb, and cell get some of the factors like the concentrated magnesium rate and the resultant calcium concentration versus ATP production rate was then determined. How to rate into it and then see what a super science calcium would do to it. But in that case, where would the cupcakes have gone? But what about the cupcakes? Oh, here are my citations. That's my presentation. Okay, bye!
Well, class dismissed.